So we're doing this one problem here from a past quiz. You will have a quiz on, not today, of course, next Friday, right? Whatever I'm doing, I'm screwing it up. I screwed it up somewhere. But again, maybe you see it at the end. You could have you could have a leading 15 or a leading negative 15 or a leading 3. It doesn't matter. All of them would be counted the same. And I just screwed up my sign somewhere, didn't I? Yeah. And then I have it opposite. It's okay. So, but what do we get as a final answer, right? Whether you took out the negative 5 or the positive 5, I don't care. But y prime turned out to be 3x minus 1, 2 minus x quantity squared, and then an x minus 1. So some of you, if you don't have, so you could have just the positive 15 out here, and then this factor would change, right? You'd have a 1 minus x. Does everybody have one of those two answers? Nice. Nice. Everyone, anybody else need a little more time? A little more time, okay. And I already see where I screwed up. I realized I forgot my negative and I added it the wrong spot. So it should be there. So while you're still working, I'm going to put this on Desmos because I want to take a look at the original function. So looking at that, I had quantity 2 minus x, that quantity cubed, times 3x minus 1, that quantity squared. if you remember from pre-cal, about multiplicities of zeros, does that sound familiar to anybody? Multiplicities of zeros. So notice I have here a 0 of +2, right? And it happens 3 times. So at the number +2 on the x-axis, it goes through and it looks kind of cubic. I have a 0 of 1/3 with a multiplicity of 2. So at 1/3, I hit the 0 and bounce back off. When I have even multiplicities, I bounce, right? The function bounces. Odd multiplicities, the function goes through. Does anybody remember that? Right? Now, look at my derivative. Right? Look at my derivative now. What are my critical values? Critical value of 1, critical value of 2, a critical value of 1/3, right? So look at what happens at 1/3 on the curve. Notice I'm skiing on that hill. I come down to that very bottom part on the x-axis, and my skis are horizontal, right? So the critical value gives me a place where I'm going to have a horizontal tangent. I had a critical at 1 as well. And notice I'd be at the top of that hill again, my ski's horizontal to the ground, right? And then finally, it looks like here, maybe I'm skiing down there and there's one little ledge, right, where my skis are horizontal, and then again, I'm moving back down there, right? Nice. I had a question from Jack to do. Let me do that problem. Thank you for emailing me the problem. If you notice, I'm going to have a quotient rule, right? You can see the quotient, yeah? But I'm also, look at the denominator, it's a product, so I need a product rule inside of a quotient rule. So we start with just the quotient rule. First upstairs function is 2x, derivative is 2. Downstairs function is sine x tan x. And my derivative needs a product rule, right? So I'm going to do another little loop on the side. So sine x, derivative is cos x. Tan x, derivative is secant squared x. So my derivative, back to my quotient loop, right? I need to put this product loop in. So sine x, secant squared x, plus cos x, tan x. Now that can be simplified, right? So I want to be careful here, but I also know I need the downstairs squared for the quotient rule. Jack, okay there so far? Yeah, so you see, I just did over on the side, I did that product loop that I needed. Trying to keep things as clean as I can. So it looks like I have 2 sine x tan x minus 2x times the quantity sine x secant squared x plus sine x. If I can simplify a little bit there, I will. So you see the cosine and the tangent cancel there. All over sine squared x tan squared x. So, and my goal here is really to, this is like I'm going back to pre-cal where I had to verify trig identities. First thing we taught you was turn everything into sines and cosines and try and simplify, right? Or factor. So for sure I can factor out a 2 sine x from upstairs. And then I still have my sine squared x tan squared x. But then what's left over upstairs is not so easy to see sometimes. But I certainly have a tan x. And I took out this 2 and these signs, so I still have minus x times secant squared x plus 1. Not so pretty, but again, you're kind of cheating with the solutions. You have a solution, and you know where the book wants you to go to, see if you can get there, right? This sign cancels with that sign. So 2 over, oh, that's a tan squared, sorry. That's now just a sine. And the question is, can I simplify anything in here? Not quite sure yet, but we'll see. Tan x minus x secant squared x minus x. Not really. I don't think I can do much in there. Say again? One more time? Yeah, and again, you're kind of using the book to train yourself. What is a car or a truck, right? No one ever thought of that. But when I'm walking down the street with my pop, and I said, I said, look at that cool car, and smack me and say, no, that's a van, right? So eventually, you look at enough solutions, you'll realize when you can go more or not. Jack, did you have another one you wanted me to do? Anybody else have one for me to do? You're going to email me, right? We got a nice, short, easy class today. Done at 12 today. If you want to talk to me at the end or you need me for something at the end, that's fine. While Jack's sending me that, we have homework due Monday. 6 problems. Feel free to take paper. I bring paper for you on purpose. If you don't have paper at home, you don't want to rip it out of your notebook. So 6 problems, 2 from 3.3, 3.4, and 3.5. And the special piece on 3.5 is you're not going to get a nice looking derivative. So just get me a slope, right? How do you do that? You're just going to plug in the numbers, right? Everybody got that? Nice. Yes? Yeah? You okay? Yeah, feel free to take paper, please. Don't feel bad about taking the paper. Jack, thank you. Yes. Yeah. So I have to do the first to get there. So this is another one from Jack. It's x cubed plus y cubed equals 1. Is that correct? I have no idea what it looks like, but let's find out. X cubed plus y cubed equals 1. Nice. Very cool. What are you noticing about where I'm skiing and I either am calm as hell or screaming, right? You see any spots where I'm calm, where I'm flat on the ground, right? Or when it's so steep, I've probably fallen off a hill, right? So definitely here, it looks like I'm nice and calm, right? Here, I'm definitely screaming, right? So I'm looking for where is there a horizontal tangent, where is there a vertical tangent, where is my derivative 0, where is my derivative undefined? That's what I'm looking for. This is chapter 4 stuff. I can also look at concavity here, kind of the bend in the curve. Concave up is like where you can drink out of your hand, right? So you can see it's kind of a bend, like a smile up here. Concave down is like a frown. So when the second derivative is negative, my curve is concave down here. And then back again, concave up. You can kind of see the top end of a smile, right? The second derivative is positive. Positive people smile. So Jack, they wanted a first derivative and a second derivative? Yeah. So first derivative, right? And we're saying, okay, d dx of x cubed plus d dx of y cubed equals d dx of 1. So the first piece and the last piece are easy. This is 3x squared, right? And what about the y cubed? It's 3y squared, but the inside is not x. The inside is y, so the derivative is y prime. And this one's not too bad to solve for y prime, right? I get what? 1 minus 3x squared over 3y squared, right? So look at that. Where is the upstairs equal to 0? Right? Where's the upstairs equal to 0? When x squared is 1/3, right? Yes? When x squared is 1/3, or x is square root of 3 over 3. When is the downstairs equal to 0? When y is 0. So look at my curve again. Robert, just Robert, yep. What? Oh, thank you. Silly Robert. That makes much more sense. Thank you. All right, so minus 3x squared. Oh, sorry. Y prime is. Got to help me today. I'm not having a hard time here. Minus 3x squared over 3y squared. Yes. Okay. So y prime is minus x squared over y squared. That makes it easier. X is 0, y is 0, right? Those are my criticals, yes? Sorry about that. Yes? Everybody with me? Look at my places. When x is 0, the numerator is 0. When x is 0, I've got a horizontal. This is when y is 0. I've got a vertical. Okay, they want second derivative though, right? Pretty easy quotient rule here, right? So my upstairs function is negative x squared, derivative is negative 2x. Downstairs function is 2y squared, derivative is 2y y prime. Is that okay there? Yep. And downstairs squared is y to the 4th. So y double prime is this minus the other. So negative 2xy squared plus 2y x squared y prime all over y to the 4th. And of course I could put y prime in because I already got the first derivative, right? So let me do that. Y prime was negative x squared over y squared. Jack, this okay? As I try and simplify this, I'll see I get one of my y's to cancel, but I still have x to the 4th over y. And my choice is always to clear with LCD. So I get negative 2xy cubed minus 2x to the 4th over y to the 5th. And of course, I could factor out a negative 2x. And that's what they should have for their second derivative. So what was it, Jack? The organization in the first problem. And this one is just the y prime. Okay. You might have switched. Yeah. Nice. Anything else for me to do? Yeah. Yeah, when I did my second derivative, I got a y prime, but I got that y prime in the first derivative, so I put that back in. Nice. Let's finish the problem. I don't think I quite finished the problem at the end of the last class, right? So let me do that one. So I'm looking at, this is probably my favorite problem to do for this implicit. So expect to have it. Once I see a trig, I know I have a right triangle. I should create the triangle, and I want to see your triangle on the test. When I give you a trig, I want to see the triangle, whether you use it or not. So once I see, I can really think of this as tangent of theta equals x, which means I have a right triangle with an angle of theta and an adjacent side of x, opposite side of x, adjacent side of 1, and the remaining side as a c, a hypotenuse, right? And I can solve for c, saying 1 squared plus x squared is c squared. C squared is 1 plus x squared. C is the square root of 1 plus x squared. So now I have my triangle. Yes? Everybody okay? The triangle piece bothering anybody? Really? No, that's great, because you need it in Calc 1, Calc 2, diffie-qs. When you see a trig, you're going to be thinking, oh, okay, I should be able to draw a right triangle. So now my problem is I have tan theta equals x. I want to find y prime, right? So find y prime in terms of x. So what am I going to do? I'm going to differentiate both sides, right? So I'm going to take the derivative, or the operator ddx, of tangent of theta, and that should be equal to the derivative of x. And I'll try not to make that same mistake. The derivative of x is 1, right? Derivative of 1 is 0. So what happens on the left side? What's the derivative of the outside function, the tangent function? Very good, class. Secant squared theta. But then I need the derivative of the inside. The inside function is theta, right? So I need theta prime, and that should be equal to 1. What was theta? What is theta, right? So theta is x plus y. So what's theta prime? 1 plus y prime, right? So now I have secant squared theta times 1 plus y prime is equal to 1. Everybody with me? Nice. I could distribute here, but the easier thing to do is divide. So 1 plus y prime equals secant squared theta. Sorry, 1 over secant squared theta. Right? But what is that? That's cosine, isn't it? So 1 plus y prime equals cos squared of theta. And y prime is cos squared theta minus 1. Nice. That's a pretty acceptable answer. Of course, I could simplify it, but my directions were to get it in terms of x, right? Anybody recognize this identity? Almost negative sine squared, right? Right, because it's 1 minus cos squared is sine squared, right? So this is the opposite of that. This is a better answer, but again, I want the answer in terms of x. So I'm going back to my triangle now. Oh, this is sine squared theta, sorry. And what do I have here? I have x, I had 1, I had square root of 1 plus x squared. My ratio for sine is using these two sides. So I get y prime equals the opposite of x over square root of 1 plus x squared, quantity squared, right? Because it's sine squared. So y prime is the opposite of x squared over 1 plus x squared. Look at the first box. What would you say it's solved in terms of what? Solved in terms of cos theta, right? What about the second box, solved in terms of sine theta? What about the third box, solved in terms of x, right? You with me? And I could say, what about solved in terms of tangents? Tangent theta. What do you see? Remember, our original problem was tan of theta is x, right? So I've got minus tan squared theta over 1 plus tan squared theta. Solved in terms of tangents. So on the quiz or on the test, I'm going to say, hey, solve it this way. And so it's just about, can you make it a puzzle and figure it out by using some identity, using some algebra, right? But we'll use this triangle quite a bit. And I want to see it every time I give you a trig. You might not need it. You might not be able to finish the triangle, but that's your thought. If I get a trig, I should be able to draw a triangle. Nice. All right, here we go. New stuff. I am recording. I didn't record the morning class, so I promised them I would record this one. So we're looking at section 5.6, inverse trig derivatives. If you have trouble with trig, then most likely you have trouble with inverse trigs. So I would go back to my pre-cal book and go through the inverse trig chapter. There's probably two of them. Two sections of a chapter anyway. So the problem here, the general problem is if y equals the arctan of x, and please remember that's the same as inverse tan of x, right? I just prefer to write the first version of it, arctan of x, instead of inverse tan of x. They're the same function. Find y prime, right? So that's my problem here in this section. If I have y equals arctan x, I want to find the derivative, okay? But the problem is I have no idea what to do. But I know the derivative of tangent, right? So what we do is we take our y equals arctan x, compose both sides with tangent, right? So tangent of y should equal tangent of the arctan of x. And what happens on the right-hand side? Jadri, what happens on the right-hand side? What does it simplify to? Chrissy? Chrissy, you there? What does it simplify to on the right? Point? Just x. Because tangent and inverse tangent, right, tangent and arctangent are inverse functions of each other. Yes? You with me there? They're inverse functions of each other. Meaning, if I said tangent of pi over 6, right, is rad 3 over 3, then arctan of rad 3 over 3 is my pi over 6, right? You remember doing this before? I got 1 nod, 2, 3, 4, 5, 6. All right, 6 out of 19, that's not bad. But at this point, I'm ready to do my derivative, but I have to do it implicitly, right? Do you see that? I have to do d dx of the tangent of y equals d dx of x. On the left-hand side, we just did this problem. Derivative of tangent is what? Very good, class. Secant squared of y, but then I need a y prime, right? And that should equal 1. Derivative of x is 1. So y prime is 1 over the secant squared of y. But that's what 1 over secant squared is? Cos squared. So I've got cos squared of y. I'm going back to my triangle, right? Back to my triangle. And the cos ratio is involving these two sides. So I get y prime is 1 over square roots of 1 plus x squared quantity squared. So here it is, y prime is 1 over 1 plus x squared. I do simplify this section by only giving you arc sine and arc tan, okay? So inverse tangent and inverse sine functions. I don't bother with the secants, cosecants, and cotangents. How are we doing here? Are we okay? Well, take a look at the inverse tangent curve. Take a look at my inverse tangent curve. Y equals arctan of x. Do you see the tangent curve there? Do you see the tangent curve there? Kind of twist it around. What I'm going to do is rotate 180 degrees this way. Okay? Right? Like a bike tire, bike wheel. And then 90 degrees this way. You can see the tangent curve. Right? When we're looking at inverse functions, we're looking at the reflection about that line, right? So y equals tan of x. So you see that, and we're only dealing with that one around the origin, right? So you see the tangent function, and you see the reflection of that over y equals x, and you get the inverse tangent function. Take a look at that inverse tangent function again. Is it ever vertical? Does it ever have a vertical slope on it? Are my skis ever straight up in the air if I'm skiing on this slope? No. Is it ever zero? No. Look at the derivative. Look at the derivative, right? Look at this derivative. Is the numerator ever zero? No. So no horizontal tangent. Is the denominator ever zero? No. So no vertical tangents, right? I'm moving us into chapter 4 here as I'm talking about this stuff. All right. I want this shortcut on your formula sheet. I probably want both of them, but if y equals arctan of x, y prime is 1 over 1 plus x squared. All right, so the weird thing about this is now I have derived this formula, okay? I have derived this pattern for the derivative. If I give you this function, all you have to do is find x, well there it is, duh, and put it into this x folder, x squared. So, but you are human, so you're going to make it more complicated than that. But all I'm saying is identify x, right? It should be a little bit more confusing, but this is the one we really need to know. Y equals the arctan of u. Now I'm saying there's a function inside. Again, my only chore now is to identify what that function is and plug into y prime equals u prime over 1 plus u squared. We've been doing these processes to get derivatives. In this particular section, it's very, very simple process. So simple that you're supposed to do something else. But all I'm saying to you is identify u. Then find what? Find what? The derivative and u squared, and then plug in your derivative. Then make it look nice. In quotes, make it look pretty. All right, here we go. First example problem. I'm going to say find y prime in terms of x for y equals arctan of x squared. So this is our problem. Let's look at the curve first, okay? Y equals arctan of x squared. Let's look at the curve. So, and you can kind of see what's going to happen. The negative pieces from arctan are going to turn positive, right? Because I'm squaring them. Yes, you with me? So, any place where I'm skiing on this, my skis are completely vertical and I'm screaming and probably falling off the mountain? No. Right? Is there any place where my skis are horizontal where I feel good? I'm safe. Yes? When x is what? 0. So let's keep that in mind when we do our derivative here. Remember what I said, all I have to do is identify u. I've got this memorized or on my formula sheet. Y equals the arctan of u implies y prime is u prime over 1 plus u squared. So all I have to do in my problem is identify u as what? X squared, Robert. That's good, class. X squared. And what's u prime? Oh, nice. I didn't have to do the voice. And what's u squared? X to the 4th, right? So now all I'm doing is plugging in here. So y prime is 2x over 1 plus x to the 4th. Done. We know how to check this on Desmos, right? Yes? But we're going to check in the book most of the time. We're going to do problems fast. When is the derivative equal to 0? In the numerator, 0. So x is 0. We already saw that, right? When is the denominator equal to 0? Never, right? So there's no place for a vertical tangent. There's one place for a horizontal tangent. There are two other formulas that you should know. And then we'll look at some problems here. I have suggested problems in 3.6 from number 1 to 41. If you haven't done your inverse trig stuff in a while, make sure you do 1 through 11 for sure. Everyone else can just go to if you know your inverse trig stuff, you can just go to your derivative problems. I'll get homework for that for not this Monday, but for next Monday. I'll have something from 3.6, 3.7, 4.2, maybe even 4.3. So our shortcuts that we want are 3 of them. The first one I derived for you. The second one and the third one I'd like you to derive. I'd like you to do exactly what I did and make sure that you verify that these are the formulas. So, look at the difference between arcsine and arccosine, the derivatives, right? What's the only difference? The negative, right? And remember my wheel, right? Cosine to sine, I need the negative. If I'm starting with some kind of cosine, I'm going to get the negative. If I'm starting with a sine, I'm going to keep it positive. Same thing, right? So I want you to derive the arcsine formula, this one. So what are you going to start with? Y equals arcsine of x. We want y prime, right? But we don't think in terms of inverse trig, do we? No, we don't. We think in terms of trig, so I turned it into a trig. Once I have a trig, then I have a what? Triangle. So I use my triangle, I get the sides. Obviously this side's going to be x, and how big will the hypotenuse be? 1. The sine is the ratio of opposite over hypotenuse, so x over 1. Right? Et cetera, et cetera, et cetera. Make sure you do that. Yeah? Yeah? Yes. Is that okay? Right, so you saw me derive the trig, the tangent one, right? The arctan. I want you to derive these two. Nice, let's do another problem. Let's see. So find y prime. Let's do the secant of the arctan of 2 over x is equal to y. Well, you see a trig, yes? So I'm saying if you see a trig, you should see a triangle, but I want you to be careful in this situation. I have to notice that I have theta equal to the arctan of 2 over x. And that's where I want to get my trig from. All right, so here's our new thought. If I see an inverse trig, I see a trig, I see a triangle. If I see a trig, I see a triangle, right? But I want to make sure that I look for the inverse trig first. If I see an inverse trig, I see it, right? If I see an angle, I see an inverse trig, I see a trig, I see a triangle. I want the triangle showing up on your quizzes or tests, okay? You might not have to use it. You might have to use it. All right, we're ready. Oh, sorry, I didn't get my triangle, right? So instead of theta equals arctan, what am I going to say? Tangent of theta is what? 2 over x. So I see a triangle already, right? Right triangle. Height is 2, base is x. Remaining side is what? Square root of 4 plus x squared. Is that okay? Right? A squared plus b squared equals c squared, right? Good. Now I'm ready for the problem. Are we okay with the triangle? Nice. Okay, good. So derivative. So what do we have again now? We have y equals secant of theta, right? And we're doing the derivative of both sides. On the left-hand side, I get y prime, right? Implicit. We've been doing that for a long time. On the right-hand side, what do I get? Good class. Secant of theta times tangent of theta times what? Chain rule. What's the inside? Theta, so theta prime. I have y prime equals the secant of theta times the tangent of theta times the derivative of arctan of 2 over x. I told you we got a new process. If I'm doing the derivative, I need a prime there, right? If I'm doing the derivative of that, I only have to identify what? U. Me. U. I have to find u. I have to find u prime. I have to find u squared. I have to find u. I have to find u prime. I have to find u squared. I have in my notes y equals the arctan of u gives me y prime is u prime over 1 plus u squared. So all I have to do is identify u, which is what? 2 over x. I have to find the derivative, which is what? Should be quick. Negative 2 over, good, x squared. That should be quick. You should know that 1 over x derivative. U squared is 4 over x squared. Nice. Back to our problem. Y prime is secant of theta times tangent of theta times 2 over x over 1 plus 4 over x squared. Oh, sorry, negative 2 over x squared, 1 plus 4 over x squared. Right? U prime over 1 plus u squared. Well, I look in the book, and there's definitely no fractions within fractions. There's also no trig in my answer, because I want the answer in terms of x. So now I'm referring back to my triangle. Oh, no, I had arctan, right? Arctan, sorry. So I had x in 1 and square root of, oh, sorry, I had 2 and x and square root of 4 plus x squared, right? So I can get the secant from here, right? We agree? So that's hypotenuse over adjacent. I can get the tangent from the triangle or from my original problem, which was just 2 over x. I didn't need the triangle there, right? You see what I mean? Sometimes you need it, sometimes you don't. Times my derivative of the arctan. And on that one, I'm going to clear out fractions with an x squared over x squared. Don't let me lose you here. We're okay here? So it looks like I can simplify a little bit. 2 square roots of 4 plus x squared over x squared. And this one's going to give me a negative 2 over x squared plus 4. And you can see I have a common factor there, so I'd want to simplify that as much as I can. Using the fact that I have a rad x over an x, which is a rad x over a rad x, which is a 1 over rad x. And we don't care about rationalizing anymore. Yep. Don't care about rationalizing that denominator. So this new arctan thing, or arcsine, or arccosine, you just need to identify the interior of the function and plug into the formula. You're going to feel like you're skipping, right? Because every other derivative was a full process. This one is just find that interior piece and then go to that formula. How we doing? You got a lot to do. I know. Once we get the chain rule, things start to kind of go real fast. So you have to be practicing, right? I couldn't do implicit differentiation until I couldn't do the inverse trigs until I had implicit differentiation, right? I couldn't do implicit differentiation until I had the chain rule. So I got two very dependent things on each other that you probably haven't even started on yet. You got to get into your chain rule homework. You got to get into the implicit. You have those due on Monday. got to get into this inverse trig problems. Again, my suggested problems in 3.6 are 1 to 41 odds, of course. We also have a schedule here, right? So we're doing 3.6 today, Monday 3.7, Wednesday 4.2. I'm just going to be asking you for derivatives and critical values. It's nothing new. You have a quiz next Friday. I have midterms grades due on that following Monday. So I'll update your homework scores and your quiz scores and then update your current grade, and that's what's going to be your midterm grade. The purpose of the midterm grade is almost nothing. If you're going to meet with a counselor, guidance counselor, advisor, and you have to schedule for next semester, if they see you have an A, B, or C in Calc 1, they'll put you right away into Calc 2, okay? Otherwise, advisors can see them, no one else. You can see them, so if you have an F or a D, it's like saying, hey, let's go, let's get serious, right? That's the purpose of the midterm grade. Of course, if you're early college, you don't care about schedule. It's all set for you. There's nothing to think about. But the following week, we'll do 4, 3, and 2 pieces. And then the Wednesday before the test, we'll review, just like last time. Nice. Trying to think if I forgot anything. I don't think I did. So we're all done for today. Have a great day. Yes, Nathaniel. The quiz is product rule, chain rule, implicit, tangent lines, derivative as a limit. Yes, the last question? Yeah. No inverse trig yet. No, because I want you to practice and ask questions Monday, right? Am I there? Boy, yeah? Is that okay? Yeah, feel free to take some paper if you need paper for homework. Product rule, chain rule, product rule, quotient rule, chain rule, implicit, and then any of the old stuff, tangent lines, limits, a derivative as a limit. Boy, I'll go right back to it, okay? 1 second. Just want to stop my recording.